Hello, welcome to this online training on AC analysis in Saber RD and Saber EXP. In this video, you will see Saber solutions offering industry-leading speed and accuracy for AC analysis of power electronic circuits. You will also see how Saber provides a comprehensive solution to perform AC analysis based on the typical V-diagram of power electronic product development flow. The AC analysis is used to evaluate the stability of regulation loops of switched mode power supplies as well as the stability of networks of power supplies. Stability criteria like phase and gain margins or the Middlebrook impedance criterion can be applied to the Bode plots produced by the AC analysis. In steady-state operation, switching DC to DC power converters cycle through a sequence of configurations, each corresponding to a particular state of the power semiconductor switches. For example, here is a flyback converter. Due to the absence of a fixed operating point about which the circuit equations can be linearized, the basic AC analysis of Saber or SPICE is not readily applicable, at least not without deriving an average model that abstracts out the switching behavior and constructing a duty cycle signal. But this derivation can be tedious and needs to be repeated with every new converter topology. For the switching circuits, assuming a periodic regime, any large signal analog quantity can be represented by a Fourier series. When a small harmonic perturbation is injected, the resulting perturbation of any signal of interest is not a pure sine wave in general. Beside the injected frequency, it includes frequency components corresponding to intermodulation products between the injected frequency on one hand and the switching frequency and its harmonics on the other hand. The frequency plot of signals is produced by extracting out the amplitude and phase information at the injected frequency. This extraction can be tricky, and we will show you next how several AC analysis methods do that. On the left, we have time domain methods that are experimental in nature and that include single-tone and multi-tone. On the right, we have an analytical frequency domain method that is exact but only applicable to piecewise linear circuits. Let us first look at the single-tone method. It consists of the following steps. The unperturbed circuit is simulated up to steady state. Once in steady state, the small signal sinusoidal perturbation is injected into the circuit, and the transient simulation is continued while performing Fourier integrations of output signals of interest and monitoring their convergence. The simulation is stopped as soon as the average values of the gains and phases of the output signals over successive periods have all stabilized below a user-defined error criterion. The result is a complex number that corresponds to one frequency point in the Bode plot. This process is repeated for all frequencies in the spectrum. Now, let us look at the multitone method. The unperturbed circuit is simulated up to steady state. Once in steady state, a multi-sign signal consisting of all frequencies in the spectrum of interest is injected in one shot, and a single transient simulation is performed for a duration that corresponds to at least one period of the smallest frequency in the spectrum. Note that more than one period can be simulated to average out the results and filter out numerical noise coming from the transient analysis itself. After that, a Fourier integration of output signals of interest is carried out to extract the gain and phase of all spectrum frequencies. Beyond the time domain methods, an analytical method exists that turns out to be fast across the entire spectrum, but that is only applicable to piecewise linear circuits. In this method, matrix exponentials are used along with a precise analysis of the perturbed switching events in steady state to formulate the exact trajectory of the perturbed signals. This exact time domain formulation of the perturbed signals is then integrated analytically to produce the fundamental Fourier coefficients corresponding to the perturbed frequency. These coefficients are complex numbers giving the gain and phase information of the output signals of interest. Besides speed and accuracy, one extra benefit of the analytical method is that it produces the Bode plot of all analog signals in the circuit in one shot and at little extra computational cost. These three methods are available in Saber RD and Saber EXP as shown here. Now, we will see how these methods must be best utilized for optimum performance based on the typical product development flow. In a typical V-diagram of power electronic product development flow, the stability studies are carried out during the early stage of the development. At this stage, a piecewise linear simulator like Saber EXP helps to make topological and sizing decisions. Let us look at the flyback converter design here. Saber EXP uses high-performance switching PWL models and analytical frequency domain AC analysis with minimum simulator calibration and without the average model approximation. The open-loop gain of the given converter is shown here. It took less than a second to produce over a spectrum spanning 4 decades that includes the sideband patterns at the switching frequency and its harmonics. With this fast method, you can now tune design parameters interactively to meet your gain and phase margin specifications. An optimizer is also available to fit a crossover frequency target. The frequency domain method is only applicable to circuits with a strictly periodic operating point, which in principle excludes AC to DC converters and DC to DC converters with quantization in the digital control. Note that a high bit quantization has little effect on open loop gain. For the AC to DC converters and DC to DC converters with quantization in the digital control, you can use the time domain AC analysis that works on the principle of singleton AC analysis. Since the singleton method depends on a series of transient simulations, each corresponding to one perturbation frequency, the time domain AC analysis takes more time to complete even with the simulations done in parallel. The slow performance is especially noticeable on the low end of the frequency spectrum, where one period of the perturbation requires simulating a large number of switching events. Despite being slower, the singleton method matches the results of the analytical method as you can see here. You can see a speedup of 1000 plus in frequency domain method. The results from singleton method is sensitive to perturbation amplitude and can be noisy on the high end of frequency spectrum due to simulation noise. After the design has passed the stability studies with piecewise linear models, it can be exported to Saber RD. In Saber RD, you can implement simulation with physics-based models. The physics-based power MOSFET model is characterized using the power MOSFET tool in Saber RD. Characterized parts and components models make the design closer to the real hardware. The simulation using physics-based models is slower than the Saber EXP simulation using piecewise linear models as shown here. This limitation is overcome by the multi-tone method that works on a single transient simulation. There are certain drawbacks though. In multi-tone AC analysis, the tones are constructed as multiples of the start frequency of the spectrum, which necessarily leads to fewer points on the low end of the spectrum. Also, the range of the spectrum cannot exceed half the switching frequency, otherwise spectrum folding happens and with that noise. That said, this does not constitute a practical limitation since stability criteria are usually looked at below half the switching frequency. Something of more concern with multi-tone is the amplitude of the perturbation, which is a trade-off. Because all tones are injected concurrently, there is a higher risk of disturbing the large signal operation of the circuit and creating distortion, possibly from duty cycles going outside the range 0-1 or components like nonlinear inductors saturating. To avoid this, the amplitude of the perturbation should be chosen judiciously small and the number of tones as small as possible. But the amplitude cannot be excessively small neither, otherwise it falls below the noise floor of the time domain analysis itself, hence the trade-off. You can see that results from single-tone and multi-tone are matching and a speedup of 5x is observed in multi-tone AC analysis. You can see that results from Saber RD are also matching with the results from Saber EXP. To conclude, the three different methods of AC analysis available in Saber have been discussed and compared here with their respective advantages and limitations. If PWL models are sufficient, the analytical method of Saber EXP is fast and noiseless with minimum simulation settings to calibrate. Otherwise, when non-PWL and physics-based models are needed, the AC analysis of Saber RD are adequate and applicable on a switching circuit as is, without having to derive an average model. As we have seen in this video, Saber EXP and Saber RD provide a comprehensive solution to perform AC analysis during different stages of power electronic product development. Please check out our website for more details. Thank you for watching.